13.7, Part 2. In Part 1, we ended on this slide where we defined a linear approximation to a function. Let's start with this example. First, set up the function by inserting the point -1, 2. And check your work. Next, find the partials and evaluate them at -1, 2. And check your work. We are now ready to find the linear approximation. Please check your work. The plane is the linear approximation to the function as long as xy is close to -1, 2. So we can use the linear approximation to approximate the function where x and y each change by 5%. Use the linear approximation to find the approximate value of f at this point. And check your work. The 5% decrease in x with the 5% increase in y yields an approximate 10% decrease in elevation. Now that we have a linear approximation formula for a function, we can define the differential dz. Given xy, the actual change in elevation is denoted delta z. The approximate change in elevation is denoted dz. For xy near AB, delta z is approximately equal to the estimate dz. We define dx and dy. And now use the linear approximation to get the differential dz, which approximates the actual change in elevation delta z. The differential for functions of two variables extends naturally to more variables. Let's do an example. A company manufactures cylindrical aluminum tubes to rigid specifications. The tubes are designed to have an outside radius of 10 centimeters, a height of 50 centimeters, and a thickness of 0.1 centimeters. The manufacturing process produces tubes with a maximum error of plus or minus 0.05 in the radius and height, and a maximum error of plus or minus 0.0005 in the thickness. Use differentials to estimate the maximum error in the volume of a tube. I have written the linear approximation in terms of the given function and variables. I have also inserted the known values that r is equal to 10, h is equal to 50, and the thickness is equal to 0.1. That is if everything were perfect and there was no error. Find the partials. Now evaluate the partials with our radius of 10 centimeters, our height of 50 centimeters, and our thickness of 0.1 centimeters. And check your work. Put the values that you have found into the dV equation. And this is what you should get. Let's assume a maximum positive error in all measurements. Then the dV is given by this expression. This is the maximum possible error. I can simplify it or even approximate it to 3.44 cubic centimeters. If we would like to find the relative error, we would use the ratio of the maximum error over the volume if everything was perfect. And we get, with the maximum error, we get about a relative error of about 0.5%. Another thing that's interesting is the partial derivatives allow us to do a sensitivity analysis on measurement errors. The magnification error, if you look at dV, for the thickness T, the magnification error is 990 pi, and it is roughly 100 times greater than the magnification factor for the radius r, which is 10 pi, and about 500 times greater than the magnification factor for the height h.